Hey, hey, it's Dr. J. My favorite subject today is the polar form of complex numbers. I mean, math is a little bit like my children. I say they're all my favorite, but this is the cream of the crop here. This is one of the most interesting sections, I think, in the entire textbook. We don't really talk much about complex numbers in this course, right? Way back in February or something, we solved quadratic equations and we got various complex solutions, I plus or minus the square root of 3i and things like that. But we didn't do anything with them, right? We didn't really get to see them in any interesting sort of way. Well, I can't say that we're going to do much more, but at least we're going to see a lot more than you saw in the past. In fact, we're going to start right now with a picture of the complex plane. Sometimes called C. So the complex plane looks a lot like the rectangular coordinate system. What we used to call the x-axis is called the real axis. And what used to be called the y-axis is called the imaginary axis. So any number that lives on the real axis is a purely real number. Something like that. This would be a pure real number. But a number that lives on the imaginary axis, well, it'd be pure imaginary. And if we combine these numbers together, my picture is really bad. That's supposed to be 3i. Here, let's just make it look a little bit more realistic. There we go. Once I saw the camera, I realized, oh my God, it doesn't look anything like 3. It looks like more like 5. Okay, well, it really doesn't matter. But it kind of does. So numbers on the horizontal axis are purely real. Numbers on the vertical axis are pure imaginary. And when you combine them together, sort of a hybrid of real and imaginary, this number would be called complex. It's a complex. It's built out of two parts. It has a real part, A. It's called the real part. And the imaginary part, B, I. Okay. So we dissect the number into its real and imaginary parts. All right, well, that's just a picture of the complex plane. You have positive here, positive real, positive complex. Over here you have negative real and negative complex, and so on and so forth. We'll do lots of different examples. But what we're really going for today is the polar form of this number using the trigonometric angles and radii and things like that. So the polar form of this number, we have the radius, called the modulus. That would be the square root of a squared plus b squared. Just use your Pythagorean theorem. So that would be the square root of 3 squared plus 3 squared. Make sure you don't put the I into this formula. It'll screw it all up. Just take the imaginary part, b. We know that represents the imaginary part, so you don't put the I into this formula. And this will become the square root of 18, or 2 radical 9. So this is the modulus, or the radius. In complex numbers, we call it the modulus. Okay? And then you have the theta. Just using trigonometry, theta is tan inverse b over a. So theta is tan inverse of 3 over 3. Again, don't put the I into this. If you try to put I into your calculator, when you calculate the tan inverse, it's not going to work out. I'm not even going to use the calculator for this one, because you all know tan inverse of 1. What angle has a tangent of 1? Well, 45 degrees. We're going to use radians, so pi over 4. So the polar form of this complex number is R, E, I, theta. Yes, E. E is back. So R is 2 radical 9. E to the I times pi over 4. And we usually just write pi over 4i. Put the I last typically. So that would be the polar form of this complex number 3 plus 3i. Okay. So let's do some actual example. Not that this wasn't an example. Certainly this was an example. But this is just to kind of icebreaker, sort of get you into the realm of complex numbers. We'll talk more about this E exponential form of the complex number, polar form, and how it's related to sines and cosines in just a bit. Let's actually get into some examples. Example 1. Write each complex number in polar form. All right, -4. Yeah. Now you might think, wait a minute, you just said complex number. I don't see any imaginaries there. Well, this is a complex number with no imaginary part. So this is a pure real number. But it's still considered complex. It just means that it has no I. Yeah. So if you don't see an I, it's invisible. Pure real numbers have an invisible 0i. Okay. So -4 would be over here. The modulus, now you don't really have to do this, but I'll do it one time, I guess. R is the square root of -4. You're going to feel silly. I already feel silly doing it, but -4 squared plus 0 squared. Square root of 16, which is just 4. So in the future, when you get a pure real number, the modulus is the same as the absolute value of the real part. Yeah. So that was relatively easy. We probably could have done that just by looking. And then our angle, again, you could do it. Theta is tan inverse, blah, 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 but it's not necessary. If you already know it, I'm not even going to do it. You know that theta is pi. Yeah. Not only that, but if you try tan inverse, watch what happens. Oh, what was it? B over A. So B is 0, and A is -4. So you're going to get tan inverse of 0, and that would give you 0. So sometimes the calculator really misleads you. Remember, the tangent inverse function is restricted between -pi/2 and pi/2. So you would never get an angle of pi using the inverse function. So you need to be careful when using arctan. Arctan is another way of saying tan inverse. Remember, arctan only gives you a value between pi/2 and -pi/2. So you're never going to get an angle outside of that range. Okay. It's supposed to be a 2 there. I'm not sure if you can see that. All right, we're basically done. So the modulus would be, so we R, E, I, theta. So the modulus is 4. The theta is pi. You can leave it as I pi if you like, but most of the time we put the I last. So how about 2I? 2I. So again, if the point is either pure real or pure imaginary, you don't need to use the formula for modulus. R would just be 2. If you want to use the formula, you certainly can. Yeah, it'd be the square root of 0 squared, because their A is 0, plus 2 squared, so it'd be the square root of 4, which just goes back to being 2. So if you have a pure imaginary number, that means there's an invisible 0 in front of the I in the real part. Okay, and then clearly you can see the angle here. The angle would be exactly 90 degrees, which would be theta, so we're going to do pi over 2. Okay. I need a spot to write my answer here. Let's put it right here. So it'd be 2e to the pi over 2I. Be careful that the I doesn't drift down into the denominator. It's technically pi I and then over 2. If you want to be really careful, you can put the I upstairs with the pi just to make sure. Because if you type it and that I ends up down in the denominator, you're going to get frustrated. It's going to mark it wrong. Okay. How about -5 plus 7i? You don't even really have to draw the picture. The picture is just giving you the idea. So what's r? Well, this time I better do it, right? The square root of -5 squared plus 7 squared. So that's the square root of 25 plus 49, square root of 74. There's our r. And then our theta. Now this is where it gets weird, okay? So I'm going to go tan inverse. I'm not going to trust this because it looks like it's more than pi over 2. Tan inverse of 7 over -5. Yeah, b over a. This time I am going to use a calculator. So I've got 7 divided by -5. So that's -1.4. And then I'm going to do my tan inverse and watch what it does. I have it in radian modes. It's going to give me -0.95054, blah, 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 blah. This is in radians. All right. If you prefer degrees, you can divide this by pi and multiply it by 180. It's about 54 degrees, approximately. So that doesn't make any sense, right? 54 degrees would be down here. So don't trust it. It's not really negative. That's why the picture is kind of helpful. This is a reference angle, so we know that this is 54 degrees less than 180. So you have 180 minus 54 degrees would be the actual angle for theta. So the 54 degrees is a reference angle. ref angle of 54 degrees. I don't really want my answer in degrees. I know that most people, when they read this, you're like, what the hell is that, right? It doesn't look like an angle, all right? So we're going to keep it in radian mode, so we don't want that. We want pi minus 0.95054. So pi minus 0.95054. 2.19 will probably be good enough for this section. I think I'm doing 2 decimal places. Otherwise, these answers get ridiculous. Okay, so now the polar form of -5 plus 7i is our modulus. That's our r. Square root 74 e to the 2.19i. So if you just see a real number up in the exponent, that's implied to mean radians. I mean 2.19 radians, which is a little more than 110 degrees, maybe 114 degrees. My general principle is 1 is 57, if you'd like to just have a number in your head. So this was 54. You see how it was less than 1? Its magnitude was less than 1. Its absolute value was less than 1. All right, so that's the polar form of complex numbers. It probably hasn't gotten too exciting yet, but we just have to get into the topic a little bit. Let's go the other direction before we can see what's actually going on. Let's go the other way. Right, the complex number. How about 6e to the pi over 3i in a plus bi form, also known as rectangular form. This is called rectangular form. In other words, go back the other way. Now, we're not going to use polar graph paper in this. I'm just going to use rectangular whiteboard graph paper here. So 6 is the modulus, pi over 3 is the angle. So you got pi over 3. And then you have your triangle. Your radius is 6. So you have B is r sine theta. That's the complex part, the imaginary part. And then you have A. It's the same formula as x and y from the polar form. It is x and y. We're just calling them A and B because it's a complex number. We don't want to use x and y. It's misleading, right? X and y are implied to be real numbers. All right. This is a complex number. Well, it's comprised of a real and an imaginary part. So B would be 6 sine pi over 3. That'll be 6 times root 3 over 2. So that's 3 root 3. And your A would be 6 cosine pi over 3. I'm being really careful today. I've screwed this up several times in the past. Hopefully I've made all my corrections. So you've gotten all the corrections. Thank you for your watchful eyes. A cosine of pi over 3 is 1/2, so that one comes out nice. So the answer is 3 plus 3 root 3 and then I. Be careful and make sure that the square root symbol doesn't accidentally or unintentionally cover the imaginary letter I. Imaginary number I. I shouldn't call it a letter, it's a number. Okay. So we've kind of established something, that polar form REI theta, if you convert it to rectangular form, if you like to have a recipe here, people enjoy a nice simple recipe. A would be r cosine theta, and B would be r sine theta, and then times I. We sometimes, to make sure that we're not confusing where the I is, because the I is actually happening outside of the trig function, we sometimes write it this way. So that you don't accidentally multiply the I and the theta. I know you probably wouldn't, but you never know. If you're writing too fast, or if you're on autopilot, you're not thinking about what you're doing, you might end up with something like that. So this is our recipe for polar and rectangular form. All right, so now we're actually going to get into the thick of it. Example 3. What is this good for? Why do you need to know this? Why can't I just, write my complex numbers like I always did, using square roots of -1 and things like that? What's the advantage to doing it this way? Well, there are several advantages. Two in particular that we're going to talk about today. I mean, there's probably hundreds of advantages to this notation, but in this class, it's the last week of lecture. I'm only going to give you 2, all right? Powers. Suppose I wanted to raise a complex number to a large power. Yeah. I could just do it. It would not be fun. Yeah. It'd be 2 plus 3i, 2 plus 3i, 2 plus 3i, 2 plus 3i. By the way, if on the test you forget the formula or you don't have a good example to look at to help guide you through it, this is the way you would have to do it. All right. And if we were in class and we were taking an in-class quiz or something, I would say, well, if you get desperate, do it this way if you can't remember the formula. And that's kind of your punishment for not remembering the formula. But hopefully we can avoid this if possible. We might even have numbers that are much larger than power of 7. I'm just using 7 as a nice example. So let Z be a complex number. I like to use the letter Z for a complex number. We have a theorem. Make sure I spell it right. De Moivre's theorem. Z to the nth power. De Moivre is a French mathematician, I believe. There's a short biography of him in your textbook. You're going to love this. Z to the n power is r to the n power times cosine n theta. Just multiply the theta by n plus I sine n theta. Now be careful with your n's. If I write this too fast, you'll write sine and then you'll forget which one's the n for the sine and things like that. So some people use a different letter like K or M or something to distinguish it. So this is De Moivre's theorem. What that means is that this is my Z. It's my Z, and I'm raising it to the 7th power. I don't have to write it twice. Yeah, so this is Z to the 7th. I am not going to do it this long way. I'm going to write it as r to the 7th cosine 7 theta plus I sine 7 theta. I got to figure out what my r is. Remember what r is? The square root of a squared plus b squared. So what's that, 13? Square root of 13? My math is right. That's 4, and that's 9, so square root of 13. You might not like the theta that you get, but it is what it is. Hopefully, if it's in quadrant 1, you can trust the calculator. It is in quadrant 1, right? Both A and B are positive, so it is in quadrant 1. Make sure you do the ratio correctly. I can't tell you how many times I accidentally got the ratio upside down and wasted a bunch of time. So you got 3/2, and then you got your arctan or your tan inverse. It's also known as arctan. And you can trust this. This is 0.98. 2 decimals is plenty for this section. And I hope that doesn't cause you any problems. If it doesn't mark it right with 2 decimals, then go back to using 4. But I think I've planned it so that 2 will be sufficient for this. Okay. So there, plug in your theta, plug in your r. So I've got, let me write my answer down here. 2 plus 3i to the 7th power is the square root of 13 to the 7th power. I'm just going to multiply this on a calculator. Cosine of, multiply this by 7, 6.88. I'm rounding to 2 decimals. Plus I sine 6.88. Now, I want to point something out. I want to simplify this as much as possible. So I'm going to simplify it. Although on your homework, I'm about 99% sure. I mean, I've only played around with this for a minute before the lecture, but I'm 99% sure that you could just type it in like this. So if you just want to be done, you know, it's May, you want to get it over with, go ahead and type it in, you're done. I like to simplify it a little bit. You got the square root of 13 to the 7th power. You know? So what happens to that? You're going to get 13 times 13 times 13 times the square root of 13. Yeah. Maybe I should write that out. Every 2 square roots of 13 become a 13. I know I don't need to explain this, but I'll do it anyway. So every pair, you have 3 pairs of square roots because there's 7, and then you have a leftover. In hindsight, I wish I would have done 8 or something like that. All right. So you got 13 times 13 times 13. So that's going to be 2197 square root 13. And then 6.28 is the same as 2 pi. So you can actually subtract 2 pi from this to simplify the angle. Now, you're not required to, but you should give me an angle between 0 and 2 pi if instructed. I don't think that is required, but sometimes it is. So if instructed to be between 0 and 2 pi, then you can subtract 2 pi from this angle. If not, you can leave it the way it is. So I'm going to go 6.88 minus 2 pi. And my final answer is 2197 square root 13 cosine. I've subtracted 2 pi, so now I have 0.59. Oh, it's actually 0.6, isn't it? Nice. Plus I sine 0.6. You might think, wow, that's a simplified answer, or that was easier than doing it the other way. Well, yeah, it really was. I'd still be talking if we were doing it the other way. And by the way, I talked through this entire example. Had I not talked so much, it probably would have got done 10 minutes ago. Okay? But, no. Sometimes we like to change this abbreviation because this is a lot to write. Another notation, it's called CIS notation. C stands for cosine, I clearly stands for I, and S stands for sine. You could write this as 2197 square root 13 CIS 0.6 or 0.60. This is what we call the CIS notation. So write the following complex number in CIS form. All right. So -5 minus 2i. It might help to draw a picture. Certainly wouldn't hurt. -5 minus 2 so that you know what quadrant you're in. Your radius is the square root of 25 plus 4. So the square root of 29. Square root of 29. Your theta, I've got to be careful because we're in quadrant 3. So tan inverse of -2 over -5, or arctan 2/5. Now arctan 2/5 is going to give you a ref angle. It's not your actual angle, it's a reference angle. Some people use a different notation. They'll call this like theta hat or something like that. I'm not going to bother with that. I don't need to introduce more symbols. So be careful, though. That's not your actual answer. So 2/5 or 0.4, and then arctan. So theta is 0.38, but that would be in Q1. We're not in Q1, we're in Q3. So our actual theta is pi plus 0.38. Because we're in quadrant 3, 180 degrees is pi. So we're adding 0.38 to our pi. So our actual theta is 3.52. Okay, so we're done. So CIS form would be square root 29, CIS 3.52. All right. Remember what that means. Just put a little cloud up here. That means the square root of 29 cosine 3.52 radians, of course, plus I sine 3.52. We want to go back the other way now. We want to take a number that's written in this form and rewrite it into rectangular form so that we have a full spectrum of mobility here. We want to be able to go both directions. Convert z equals Blurry on me. Give it a second. Convert z equals 4 CIS 5 pi over 6 into a plus bi form. Come on. There we go. Nice. I'm glad I didn't have to stop the video because then it takes me 3 hours to upload it once I stop it. So if I can get this all done in one take, you'll have your video soon. All right, so convert this into a plus bi form. Notice you don't really use the z. The z is just the name of the number. I'm calling it z, complex. So that's 4 cosine 5 pi over 6 plus I sine 5 pi over 6. You probably know these by heart. Cosine 5 pi over 6 is negative root 3 over 2. And sine 5 pi over 6 is 1/2. I usually like to distribute the 4 so that you get a nice clean answer. You're going to get negative 2 root 3 plus 2i. Well, that's the basics. So we're done with the basics now. We've got the polar form. We've got the rectangular form. We know how to do powers. And now we're going to end with the best part, roots. Find the square root. Square root of 1 minus 4i. Now, there are actually 2 square roots, so let's give the answer, give the root with the smallest angle. Because you will actually get 2 answers here. Now, I'm not sure if you've ever seen this in another algebra class. There are some algebraic techniques for finding the square root of an imaginary number. I always tell my basic algebra and even my intermediate algebra students not even to put the I under the square root because it just causes so many problems. But at the pre-calculus and calculus level, you're going to have problems that involve square roots of an imaginary, and you do not want to attempt it, I mean, unless you really want to, attempt it with algebraic techniques. You want to use polar. I mean, not that polar is not algebra, but you want to use trigonometry in order to solve this, to simplify this. So similar to the power formula, we have a recipe for nth roots. It's really Moivre's theorem in reverse. Okay? So if z is equal to r cis theta, then the nth root of z is equal to the nth root of r. Remember, a 1 over n is the same as the nth root. We read as a fraction. Times cis theta plus 2k pi over n, where k ranges from 0 all the way to n minus 1 So this gives you n possible answers. Let me call them roots instead of answers. So you start with a 0 and you stop at n minus 1, and this will give you n answers. In this problem, n is 2. So we're actually going to get 2 answers, and I want to give the one that has the smallest angle. Once we have this complex number written in this CIS form, then applying this formula is going to be a lot easier. So let's do that first. So n is 2, and z is the inside the radicand 1 minus 4i. I used up a lot of space here, but I do need this formula, so let's see if I can work up here and keep this formula for later. So I've got z is equal to 1 minus 4i. So what's r? Square root of 17. Mental math, yeah? 4 squared or negative 4 squared is 16. 1 squared is 1, so 17. What's theta? This is, again, ref. Here's a thing you could do. You can call it theta ref. Right? Just to remind you, this is not the actual theta, because this point is not in quadrant 1. Okay, so theta reference angle would be tan inverse of negative 4 over 1, or just tan inverse of negative 4. So theta reference, or reference angle, now I wish I just would have used a hat, negative 1.33 radians. It's in quadrant 4. So we want two pi minus 1.33. Because 2 pi is one whole rotation, and then we're going to go minus 1.33. I want the smallest positive angle that I can get. So that's going to be theta 4.96 positive angle. We're going around this way. I want theta to be less than 2 pi if possible. To use this formula, it's very important that you have your theta in the right form. Okay, so we're doing the square root, right? The square root of z. So the square root of z, n is equal to 2. So all of my now this is interesting. I already have a square root, so it's the square root of 17 to the 1/2 power. It's the square root of r. R is already the square root of 17, so it's the square root of the square root. Remember that r was actually referring to the inside of the radical. That's the modulus. And then you take the square root of it, so now it's doubly square rooted. You could also write this as the 4th root of 17. Same thing. It's the square root of the square root. And then you have CIS 4.96 plus 2k pi over 2. And k is going to go from 0 to 1. So there'll be 2 possibilities for k. It's kind of messy. Let's clean up our answer here. So we have the square root of 1 minus 4i is equal to the fourth root of 17. CIS 4.96 plus, now I like to plug 0 in first, so that'll be 2 times 0 times pi divided by 2. That's one root. Or the second root, so this would be for k equals 0. The second possibility would be the fourth root of 17 CIS 4.96 plus 2 times 1 times pi over 2. That would be for k equals 1. So depending on what root you're doing, if you're doing a square root, it's pretty straightforward. This is analogous to the plus or minus. But in complex numbers, we don't have pluses or minuses. You just have angles. So this gives you two different angles, two different possibilities. You just do k equals 0 and k equals 1 and simplify these as much as possible. So 1 minus 4i square root is the fourth root of 17 CIS. Notice when you plug in 0, it's just going to kill that pi. So you just have CIS 2.48. Or your other possibility, 4.96 plus 2 pi, because you're plugging in 1. And then divided by 2. 5.62. So there are two complex square roots, two square roots of the complex number. This one has the smallest positive angle. So this is the one I want in this particular problem. Sometimes I ask for both. If I ask for both, well, then give me both. Yeah. I rarely ever ask for the largest angle. I don't know why. I've never was asked it myself, so I rarely ever ask you. I either want both or I want the smallest one. That's kind of the standard. All right. Now we're on to something, right? Now we have a powerful tool here. You can take roots of any complex number. And in fact, it doesn't even have to be a complex number. It could be a real number. Find all, come on back to me. Find all cube roots of 8. Come on back to me. I don't want to stop the camera. Come back. Just give it a second. Have a water break or something. Maybe it'll come back to us. I'm determined not to stop the camera today. If you're wondering why it keeps taking me until 5 o'clock at night to get the videos up, it's because any editing that I do, if I edit the video, it takes hours in order to get it up there. So if I can get this in one take, you guys can watch this soon today. Come on, come back down to me. Come back down to me. I might have to stop the tape. Well, I'm trying to find all cube roots of 8. I'm waiting for the camera to stop to come out of autofocus. Come on down. Come on down. Come on. Come on. I got to stop the camera. Oh, I was just about to hit stop. Good. All right, find all the cube roots of 8. All of them. Yeah. There are 3 cube roots of 8. Yeah, you only know 1 by heart, right? 2, right? That's the one you know by heart. I actually would just hold that in the back of your mind. When we're done, one of our answers better be 2. Because we already know from basic arithmetic the cube root of 8 is 2. So that's the one we're going to get for free, but don't put that one down yet. Just wait and make sure that that comes out to one of your answers. You want to find all of them. Okay, so you want to write 8 as a complex number. Every real number is, in fact, a complex number if you look at it in the complex plane. So you're looking at 8 as being a complex number. And now you want to find its modulus. Well, it's clearly 8. Yeah. I'm not even going to do the math. It's the square root of 8 squared plus 0 squared, where the square root is 64, which is 8. So that's your modulus. You could have just done that in your head. All right. Now find your angle. Yeah. What's your angle? What's the angle here? 0. Yeah, you're on the real axis, so your angle is 0. Or you could say 2 pi. I always want the smaller one, so give me 0. So this number is z equals 8. That's our modulus. CIS 0. 0 degrees, 0 radians, same thing. Now we want the cube roots. So 1/3 cube roots. So that'll be 8 to the 1/3 CIS 0 plus 2k pi over n. And you're going to let k go from 0 to 2. You always stop one shy of whatever root you're doing. Yeah? So you're doing a square root, you do 0 and 1. You're doing a cube root, you do 0, 1, and 2. So on and so forth. Fourth root, you do 0, 1, 2, and 3. So we're doing 0, 1, and 2. So we're just going to repeat this recipe 3 times. That'll give us all of our cube roots. Remember, we already know one of them is going to be 2. Let's see that. So we've got z to the 1/3. Remember, z is this guy. This is z. I'm just calling it z. 8 is equal to z. You could just say 8 if you want. So I am going to put that now. That's 8 to the 1/3 CIS 0 plus 2 times 0 pi over 2. So that's 8 to the 1/3 CIS 0. Okay. Or 8 to the 1/3 CIS 0 plus 2 times 1 pi over 2. So this will be my second k, my second value of k, which is 1. So that's going to be 8 to the 1/3 CIS pi. Yeah. 0 plus 2 pi divided by 2 is just pi. And then the last one, 8 to the 1/3 CIS 0 plus 2 times 2 pi over 2. That's weird. Something funny happened. I might have to stop the tape. Something funny happened. That's not right. Ah, I found the mistake. Glad I don't have to stop the tape. Oops. N is 3. I shouldn't have erased my formula. N is 3. So this will be 2 pi over 3. All right, we got it. And then this will be 4 pi over 3. Now we're cooking. So be careful. I just almost screwed it up. You're not always dividing by 2. You're dividing by n, whatever n is. Yeah. Remember, the formula is r to the 1 over n cis theta plus 2k pi over n. N. So we're dividing by 3. I was about to stop the tape and redo the whole problem, but I saved it. And I don't have to get your emailing me that I made a mistake, because I probably will make another mistake at some point. All right, so we got 3 possibilities. All the cube roots. We actually use the symbol omega. This is a Greek omega. It looks like a W, but it's an omega. It's just a nice way to list out all your answers, although you don't really have to. You can still call them Z's. But I like to use the omega notation. So the omega 0, it kind of corresponds to what you plugged in for k. So that would be 8 to the 1/3 CIS of 0, which just is 2. That's the one we already knew. Yeah, the cube root of 8, CIS of 0. And then you've got 2 more roots. You've got 8 to the 1/3 CIS 2 pi over 3. And 8 to the 1/3 CIS 4 pi over 3. I like to simplify the 8 to the 1/3, so this is 2 CIS 2 pi over 3. And this is 2 CIS 4 pi over 3. And there it is. Those are your 3 cube roots of 8. Now, these are not in the standard rectangular form. These are in the cosine I sine form. You might want to rewrite these into another form. In A plus BI form, you got a little bit more work to do. Well, this one's easy. 2 plus 0i, that one's done. For this one, you actually have to do the cosine and the sine. So that would be cosine 2 pi over 3 plus I sine 2 pi over 3, and actually figure out what that is. Cosine 2 pi over 3 is 1/2. Sine 2 pi over 3 is root 3 over 2. So this is your second. So omega 0 is the first cube root. Omega 1 is the second cube root. I know the index is always 1 less than whichever one you're talking about. Omega 2, where are we at? 4 pi over 3. So that'll be, oh, another mistake. I'm really all over it today. 2 pi over 3, I didn't see that 2 there. 2 pi over 3, the cosine is -1/2, so -1. Good thing I caught that. So that's going to be 2 times cosine 4 pi over 3 plus I sine 4 pi over 3. I won't screw this one up. That'll be -1 minus I root 3. It's the same sine and cosine. It's just in quadrant 3, so both of these are negative. And since I started this lecture with a picture, I might as well finish with a picture. 2, that's your omega 0. I'm just going to call it 2. And then 2 pi over 3, that's your omega 1. And 4 pi over 3, all of your roots will always lie on a circle, and the angle is always the same between all of the roots. That's your 120 degrees. So it's a cube root of 8. So the cube roots of 8 lie on a circle. In fact, all roots lie on a circle, equally spaced around the circle. I know I didn't draw it very well, but these should all be 120 degrees around all three angles. Okay, it's about an hour, and I got it done. There's a few more higher roots, like 4th roots and 5th roots. Give them a try. Tune into office hours on Zoom if you have any questions. And if I get a lot of outcry, if I get a lot of people confused, I'll post maybe a little mini video that shows the loose ends, maybe some ones that I didn't get a chance to talk about today. But I want to get this up there as quickly as possible. So Dr. Jordan signing out.